So I'm a cosmologist, so the title of my talk is A Universe of Data Challenges. And so I have the pleasure to get to talk to you about essentially trying to understand the data of literally the entire universe. So that's definitely a big data problem. So I want to just start by giving you a sense of the kinds of questions that we're trying to ask. There we go. Okay. So the big questions that we're trying to get a hold of are really big things like, how did the universe begin? Can we understand the physics of the universe's earliest moments? What is the universe made of? Can we understand the dark matter that we think makes up about 85% of the universe? And what is accelerating the universe? So we think the expansion rate of the universe is actually speeding up. We want to know, is that some new energy component? Is it constant with time, or is it a modification of gravity? And we also want to understand how the hundreds of billions of galaxies in the universe form. So what provides the seeds to start them forming, and how do they form over time? So we actually have a really beautiful picture that describes almost everything we know in the universe at large scales. And amazingly, that's based on a few physical principles and then a very small number, about 7, actual parameters. So the basic idea is that there's some moment in the early universe which created all of the fluctuations in density that later become galaxies that are able to form stars and planets. Gravity, we think, is described by general relativity. And then the mass in the universe is dominated by something we call dark matter. And we're not really sure what dark matter is, but we know a lot about how it behaves. And then we think that the universe is accelerating. So in this context, amazingly, these are all like really weird ideas, super weird. But almost everything we know about this can be described by about 7 parameters. And 4 of those parameters just describe the amounts of different kinds of material in the universe. 2 of them describe how big the fluctuations are and how those fluctuations vary as a function of scale. And then the 7th one basically describes how fast the universe is expanding. So in that context, we actually have a huge amount of data, and this data is really what has driven a revolution in cosmology in the last 20 years or so. So that picture that I just told you, when I started graduate school, was completely different than it is today. So it's been a really amazing couple of decades. The first moment of the universe is described we actually have very precise pictures of it. So this is a picture of the temperature fluctuations in the universe just about 400,000 years after the Big Bang. And these temperature fluctuations are what provide the seeds that later grow into galaxies. We can then look at what the universe looks like today, and it's very structured. It's clustered essentially on all scales. And that structure on all scales gives us a huge amount of information about how the universe evolved and what it's made of. So in this picture, this is just a picture of the nearby galaxies, and in this picture, every single dot is an actual galaxy whose position in the universe we know. Now, of course, galaxies are actually a lot more complex, and here is the deepest image ever taken of the universe. This is the Hubble Ultra Deep Field. If you extrapolate the number of galaxies in this image to the whole universe, you get a number that's of order 100 or a few hundred billion galaxies. And those galaxies are really complex. They have interesting shapes and sizes. They evolve over time. They're distributed in a non-random fashion. And all of that gives us information. So this tiny image is just about 2% of the size of the moon. So you can imagine how much data we have if we extrapolate that over the whole sky. So one of the things that I do is try to understand how we got from that first picture to that second picture. So that first picture essentially provides the initial conditions for large computer simulations we do. So we take those initial fluctuations, combine them with the amount of material, turn on gravity, and see what happens. And what happens is you get, as I said, structure on a very wide range of scales that gives us information about the contents of the universe and how it evolves. And one of the reasons we have that information is because of the size of those simulations. So those simulations have grown really rapidly in the last several decades. So on the left side, you see a simulation done in 1985 with 32,000 particles. On the right side, we did the first very high-resolution simulation of 1 trillion particles in 2014, which took several tens of millions of CPU hours on one of the largest machines in the world. So the reason that those simulations give you information is because what you're trying to do is model what the universe does in the nonlinear regime. And what you can see in this set of movies, it's not showing up great there, but what you can hopefully see is these are two different universes which have different sets of parameters. One of them actually has more matter and ends up with larger fluctuations. So if we do these kinds of simulations and then compare them to what we see in the universe, we can get information about what the universe is made of. So what is the kind of data that we get from the sky? So we're really just on the cusp of a huge explosion of data from large surveys. We've really been very data rich, actually, for the last 20 years, but we're about to see a big new explosion. So one of the surveys that I've been involved in for a very long time, which is getting data now, is called the Dark Energy Survey. The next generation, we're going to actually, instead of just making a 2D map of images in multiple colors, we're actually going to get a third dimension using spectroscopy, which is essentially, of the full rainbow of light from a galaxy. And then the next generation telescope, which is actually being built right here down the road at SLAC, is called the Large Synoptic Survey Telescope. And each of these sets, basically every 5 years, we're almost increasing by an order of magnitude the amount of data we have and the richness. So the Large Synoptic Survey Telescope is the largest digital camera ever built, a 3.2 gigapixel camera. It will take a picture of the sky essentially every 3 days. You'll get a new picture of half of the entire sky, and it'll be about 20 terabytes a night for 10 years. And so we want to figure out how to make the most sense of this data. Just to give you a sense of the improvement in the images, right now we have about 1/3 of the sky imaged at roughly this resolution. If you compare these images, this is an image from a new telescope called the Hyper Supreme Cam telescope. It's not getting quite as faint as LSST, but if you squint, you can see how many new galaxies appear there in the faint regions. And so we're going to have pictures like this of literally the entire sky. So it's going to be a really rich data set to try to make sense of. So my work is really in doing these simulations to understand what dark matter does on the full range of scales from inside an individual galaxy to literally the scale of the whole universe. Then taking those simulations of the dark matter distribution and trying to model how it will look on the sky, trying to make realistic predictions that are as close as possible as the actual measurements we get from large telescopes. And then we want to take those measurements from large telescopes and infer the fundamental physical parameters of the universe. So we're trying to take, those billions of galaxies and turn them into those things like those 7 numbers that describe the fundamental physics of our universe, and also more complicated models, for example, that tell us about how galaxies form, how stars evolve, and those kinds of things. So I hope I've already convinced you that cosmology is a data science. It's a very interesting data science. We have models and simulations that allow us to predict how the universe works on a wide range of scales. And those models are of varying levels of accuracy on different kinds of scales. And we use various approaches, including lots of different kinds of statistical inference, including machine learning, to combine those models with training data from parts of the universe which we can actually observe really well to make predictions for what the universe looks like as a whole and how to infer the parameters that determine how it behaves. One of the things that's really intrinsic to almost all of our work is really large multi-parameter inference that combines both the models and the data. And we have a lot of interesting challenges which have, I think, both similarities and differences with more typical aspects of data science. So one of the challenges is the kind of computation that we need to do. So we are actually often computation limited, and that's because the range of scales that we need to do to understand, what something like the LSST is going to measure is all the way from the physics that determines how an individual galaxy forms all the way to the scale of literally the entire universe. So we have to be smart about picking which pieces of that problem we solve and in what combination. A second challenge is that we often have really limited training data. So we can't actually observe all of the galaxies in the universe at the resolution or with the precision that we'd like. Sometimes those observations are very, very expensive with the world's largest telescopes, or sometimes even impossible. And so we have to be smart about how we use that limited training data and combine it with models to do inference. A third challenge is that we care a lot about error bars. We're really trying to tell you what is the physics of the universe, and we don't want to get it wrong. So we care a lot about those uncertainties and about correlated errors between underlying parameters, which are really fundamental. And I think that's something which probably has impact in lots of areas of data science, but is not always taken with the same care. A unique challenge that we have in cosmology is that there's only one universe. And so we can't, we can make lots of model universes, and that's what I do in a computer. I try to make as many model universes as I can and see which of them are correct. But we only have one that we can actually go out and observe. So I want to just spend a couple of minutes on these three examples to give you some specifics on some of those challenges and how we're trying to solve them. So I mentioned that we have very expensive theoretical calculations. So sometimes the most expensive numerical simulations that we run take tens of millions of CPU hours, months of time on the world's largest machines. And we increasingly need to make very accurate predictions. We're trying to predict given statistics at sort of the 1% level over very large areas of the universe. And so we have to be smart about how we do that. And so a couple of techniques that we've been using. One is smart emulation. So we basically combine a way of effectively sampling the underlying parameter space with then effectively interpolating between that set of points. And we're working on those kinds of techniques. I think they have a lot of promise for doing this at the accuracy that we need. A second tool that we use is essentially combining theoretical predictions from different scales or with different levels of physics. So an example of how to do that is that in some of the simplest numerical simulations, we just are simulating gravity. And that works really well on large scales, larger than the size of a galaxy. But once you get down closer to the scale of a galaxy, you actually care about the full hydrodynamics of the problem. And so we have to come up with creative ways of combining those kind of very expensive simulations that we can do on small scales with very large volume simulations. So a second challenge that we have is really limited training data. So one example of that, of a really fun project we've been working on recently, is we're trying to identify galaxies like the Milky Way and find the little satellites that orbit them. So that turns out to be a very hard observational problem, which has potential to tell us about the nature of dark matter. And it's hard because there's a lot of objects, and you're looking for something like a handful of objects of order 5,000. And we want to do that for many systems. And the training data is very expensive to get. So we spent about 50 telescope nights on this project so far, and we got about 30 real systems. We have a lot of non-real systems, and that also helps us learn what we don't need to look at in the future. So that's great, but we have to be smart about how we use that limited training data along with physical models to try to make the most of the data that we have. So that's just one example. And then the last example I'll give is on the in the context of understanding errors. So, there's many image analysis problems in data science. You want to learn whether something is a cat or a dog. And in our case, we don't just want to know whether it's a cat or a dog. We also want to know what's the height of the dog, how old is the dog, what color is the dog's fur, and how did it grow over time, right? So, and we want to know what is the precision on those measurements. So we had, with some postdocs here, a recent set of papers. The first one that they looked at applying this to the problem of something called strong gravitational lensing, to use simulated images to infer the physical properties of those lenses. And then we used a technique called variational inference to obtain the posteriors of Bayesian neural nets to actually get error bars on the parameters of those strong lenses. And I think that's something which probably has applications outside where we've used it. So I know I'm running out of time, so I'll just end here and say, we're really just beginning a new generation of galaxy surveys that are going to basically take beautiful measurements of almost the entire sky at very high precision with billions of galaxies. And hopefully, if we do our work right, that will allow us to learn these fundamental questions of what the universe is made of. And this is really a very interesting problem with very interesting data challenges. And part of the way forward is this combination of large computer simulations, smart choices of which models to use, and which parts of the models we can actually train directly with data from our universe. So thank you very much.
So we have time for one question. So while you're thinking and the mic goes on, I have a question for you. You're saying you're making a lot of universes.
Yes.
So have you made some that are better than the one we have right now?
None of my universes have Earths.
See, there's something wrong with your model. Okay, question from the audience? Yep, there's one in the back there.
It's absolutely amazing to see all this work that's going on. I was wondering, for physics, has there been any moves into citizen science or ways people who aren't physicists can get involved in stuff like this?
Yeah, there absolutely have, and there's been really interesting ways in which citizen science projects have really improved our learning. So the last large imaging survey, called the Sloan Digital Sky Survey, did a number of very large citizen science projects, starting with something called Galaxy Zoo, which actually now has become the label for a large range of citizen science projects well outside of astronomy. So the original Galaxy Zoo project was focusing on identifying galaxy morphology, which is a problem that turns out is much better so far done by humans than by machines. Machines are actually basically caught up by now, but that's largely based on that large amount of training data that was generated by volunteers.
Great. Well, thanks so much, Risa, for this wonderful addition to WiDS and showing something a little bit different than an Airbnb or, an Uber, right, that we're going to have later. So thanks very much again.
Thank you.
Yep.